So for lots of familiar faces here, but for everyone who doesn't know me, I'm Ryan DeMilt. I have a background in primarily artificial intelligence, but I would say a passion for sustainability, climate change mitigation, all those things. So that's what's brought me over from the computer science, computer vision world into remote sensing and Earth observation. For just over a year now, I've been working at SIG, working on all sorts of Earth observation, machine learning tasks, and it's a really exciting time. I've made this jump just at the time when there is this big surge in publications of these new models, and this is one of the publication that I piloted here at SIG for a workshop paper, the ML for Physical Sciences workshop at NeurIPS. So, to give an idea, some context to what we're talking about, if this is kind of slow for people, the presentation is made to kind of like give an introduction, no matter like what space you're at. So we have this sort of new paradigm emerging, right, of what people call embeddings or pre-trained models. There's lots of words that float around for them. But the idea is basically you have some model, some deep learning model with these weights that somebody else trained through some other process, and you're supposed to, from this model, get some lightweight summary of otherwise intractable data, right? There's these terabytes and terabytes of big collections of satellite data. It's not obvious how these bands relate to things that we care about, like land cover or crop mapping and all these things. So we're hoping that if we have these pre-trained models, they'll summarize the image good enough that we'll get the information we're looking for without having to design these whole custom systems. The problem, of course, emerges that these models are pre-trained, right? So we didn't train them. They're not specific to our data. They're specific to some general category of data, which means that our data needs to, and I put it in quotes here because there's some fuzziness to this, needs to look similar to the training data to get good results. So what does looking similar mean, and why is this a problem, right? So looking similar means you have to be, if, say, all of your training data, for whatever reason, was in because of the way the sensor was distributed is between 0 and 1, for all the channels, and then you use some different scheme where it's all in, it's integers instead, so it's 0 to 10,000 or whatever, that data is going to look really different, even if it's kind of the same underlying scientific information, and that's going to be a problem. But that example I just used is actually a relatively easy case that we have in machine learning. So you can do these techniques that we call normalization and standardization to put, just do some very simple math to put something in a compressed value range with mean and standard deviation that we would expect. Your problem emerges when you're actually changing the distribution of your training information. So in this case, this would be, say we migrate to give a look forward into the presentation a bit, say, we have a brand new satellite launched by some private company, and it's got this amazing technology on it. But because of that, the color gradients are all slightly different than we would expect in some of the publicly available satellites. The question that we set out to answer is this important? Basically, are these different satellites impactful? Is there some, is there something we need to be worried about here? So specific to the Earth observation context, right, we have all these different satellites, right? We have the old Landsats, we have Sentinel-2 starting in around 2015. We have even more diverse things like UAV data and stuff, right? All of these things generate some kind of Earth observation input, and they generate optical sensor data, which is what the vast majority of our Earth observation foundation models use. And we have a ton of options for them. And this gets even more diverse when you start factoring in something like the Planet Consortium, or even more complicated when you consider there are so many companies that provide this type of data in all these different ways, right? And while the underlying science that motivates these satellites and how they collect data is the same, the sensors are different, the underlying workflows are different, the corrections and processing are all different. So the question we had to ask is, how do EOFMs respond in practice to changing modalities or input streams? Right? So the question is, first, how do people generally deal with this in the wild? How do they even make a model work when you have changing input streams? So what is generally done is that each model has some configuration of central wavelengths of light that it can configure that is generally related to the type of data you trained it on. So for example, the sort of archetypal Prithvi model takes in the bands from the HLS training data source. There are some models such as the DOFA model, which we'll come back later, which has a mechanism to allow it. You give it the central wavelengths, and then you get back a layer that will take any configuration of bands. And then there are some other things where, for example, you can use the full Sentinel-2 collection and some SAR information. Or in the case of the Google embeddings, which are another thing that's created a lot of stir, there's also some complication because the Google embeddings actually take multiple copies of each of these types of information using the same satellite but at different processing levels, or even using Landsat and Sentinel at the same time. Generally, the way we deal with this is we say, okay, Prithvi takes RGB and these other bands, and we just match them to our new satellite. We say, okay, well, this satellite gives me these wavelengths, just plug the data in there, or in the case of DOFA, just give it the central wavelengths. And the question is, are these things really the same, right? This is a picture from DOFA's paper, and you can even kind of see in their paper that the difference between, say, a NeurIPS drone image and a Sentinel-2 image of the same place, the RGB from that Sentinel-2 is not the same as the RGB from the NeurIPS, right? You're in different atmospheric conditions. The way it's processed is very different. It seems like this should create problems. And then with satellite data, we even have this further level of problems, right? Where there are levels of processing to satellite data. Even for common collections, we have these different atmospheric corrections and moving from the raw data acquisition to surface reflectance. And the question is, should we be worried about this, right? With these new models, this hasn't come up in the past because if you train a random forest on whatever data you had around, it's only that data. It doesn't matter where it came from or how you got it. Your results are going to be your results. Another question that we've talked about is, why hasn't this come up? Why don't people talk about this in, where I come from in the computer vision world? And one thing is that the process of observing from these satellites is hopelessly complicated in some ways, right? There are atmospheric corrections, sensor angles, different resolutions, and just different physical architecture of these sensors. Whereas, and I'm sure that people who are really into photogrammetry would correct me here, but in terms of pictures like we would expect in the computer vision domain, you're generally in the lower atmosphere where all of us live. You have physical cameras that are different from each other, relatively similar, and you have a standard quantization, which is you always just take that input and map it to 0 to 255 for all the RGB pixels, and this is a relatively stable way of looking at the world. And even in that case, we would not expect a model trained on, say, a classic computer vision data set like ImageNet, where you're taking pictures of eggs and flags and other sort of mundane objects, and expect it to have really any capability to reason well on a data set like a drone image. Right? There's this understanding of domain shift. So the question is, do I need to apply this thought of domain shift where we adjust our expectations of models or come up with custom training procedures to deal with it in the remote sensing case? So there's a complication here, right? Which is these models are based on vision transformers. Their internal dimensions are these patch summaries. They're 700 dimensional vectors that are supposed to represent parts of an image. How do we compare them to each other? How do we make sense of what I'm saying here of, okay, well, do they change between satellites? What does changing mean? What does similarity to each other mean? So in this paper, we opt to look at the patches of a VIT image. So you can compare the patches to each other in a couple ways. You can measure, in this case, it's showing off the cosine similarity between them, which is just a way of showing how the vectors are aligned in their 700-dimensional space. Or you can measure the similarity of, for every image, the VIT will measure, will create what's called a class token, which is supposed to be a summary of the whole image. So you can compare the similarity of the class tokens to each other. The difference between those is a class token will tell you what does this VIT think this whole image is like, versus a patch token says, what is this little region like? Those have slightly different meanings. We have experiments that look at both of those perspectives. So we've gone through a lot, I realized. So if anybody would like to stop me and ask questions, let me know. Otherwise, I will just keep powering on until I see something. So we, like I said, we deal with this problem of scale and shift by just normalizing. It's a simple trick. It puts all the data at mean 0 and 1 standard deviation. But the problem is if there is, more underlying shifts in the distribution. Let's say some sensor is more sensitive to green light or quantizes green light in some slightly different way. So there's a broader spread of values of green. So our claim that we're examining here is that if post-normalization, the same input image at a location collected from different sensors, it returns a different result, returns non-similar either representations or representations that are similar to the wrong things, then the implication of that would be that these different responses could, and that's an important note, they don't necessarily mean that, but could imply different performance depending on the input sensor, or if you're very interested in explainability of your system, an unreliable analysis, right? Maybe it still works good, but it's working good not for a reason that maybe makes sense to you or is easy to attribute. So this is one of the main results of our paper. For those who are familiar, these graphs will look pretty familiar. This is what's called a t-SNE. It's a way of taking high-dimensional data, in this case, our 700-dimensional Prithvi embeddings, and just plotting them on a 2D graph. The way it does that is by an optimization process where it over a few rounds, moves similar vectors closer together in the 2D space and dissimilar vectors farther apart in the 2D space by our cosine similarity. So if our models were, say, agnostic to the sensor that's put in, there would be no reason to think that in the embedding space that patches from these are the CLS tokens, the CLS tokens from, say, an HLS from an HLS collection, which is a collection of the other satellites, and the Sentinel-2 collection should be any different from each other. If we're finding that these models are responding just the same, all of these colored dots, which are colored just by the sensor they came from, should be roughly intermixed, right? Because they should be differentiated by what's on the ground, by whether there's wheat there or forest or urban area. But what we find is that in a lot of cases for the embeddings of the Prithvi model, it is very, very easy to cleanly separate these embeddings from each other, with very rare exceptions, with the only exception being the Landsat 8 and 9, right? Many of us here are familiar with these collections. Landsat 8 and 9 are basically the same satellite with very few differences from each other. But in the cases of these satellites that do have very different internal architectures, Landsat 8 and the Sentinel-2, or Landsat 9 and the Sentinel-2, you see there's almost a clean line between them. You can completely separate these collections from each other, which implies that while we can't see it in the 700-dimensional space, that there is a very clear difference between them overall, meaning that they're almost probably in that high-dimensional space in completely separate regions. I saw something in the chat. Definitely reasons that Lindsay. Yes, and that's what we see, is that and this is restricted to the bands that Prithvi can take in, right? So Prithvi isn't seeing additional information in the Sentinel-2. It's seeing the same 6 bands, but just from a different sensor. And we're still seeing these differences. The natural next question is this the same for another model, particularly the DOFA model, which is a model that explicitly tries to combat this problem with their central wavelength matching mechanism. And we see that there is some mitigation, right? There's a little bit more mixing and intermingling depending on the collection, but that broadly speaking, these are still incredibly separable by sensor type, right? So you can almost imagine that in this massive space, these points are clustered completely separately from each other. Okay, so we know that now with 2 different models, 2 different EOFMs, that this is true, that have completely different training archetypes, different training data. Well, why do we care? Is there something, for example, the next question we would interrogate is this important? Are the things, say these 2 spaces are separate from each other, but that in both of those spaces, grass is similar to grass and water is similar to water, and we're all good to go? The next experiment attempts to answer that question. So this is what we call our local neighborhood agreement test. What we're testing here is in a neighborhood of each patch of 5, 10, or 20 closest neighbors to it, are these the same between 2 different sensors pairwise? How much agreement is there between our neighborhoods? And what we find is that you get generally like a 25% up to 30% in some cases difference in the neighborhood, which means that the most similar patches to you might be very, very different depending on what sensor you use for each EOFM. So this is of a lot of importance for one of the things that EOFMs are pitched for is that we can use the embeddings to give these summaries. But what we're showing here is that depending on what sensor you use with which EOFM, you get a different summary, which could end up in, say, you're doing some similarity search thing or some other such pipeline where you're just feeding these embeddings in and you're not retraining your model, that the closest or most similar patches to what you are looking at could be very different between them, which is of quite a bit of concern for the use cases that UFMs are generally presented for. So the final question we have after seeing these 2 results is how easy is it to tell these embeddings apart, right? If I gave some machine learning model, if I gave it Prithvi embeddings of HLS data and Prithvi embeddings of Landsat 8 and Landsat 9 data, how easy is it to partition these? We've seen that we can make a visualization of it, which implies that it's pretty easy. But so we trained just some simple classifiers to do this. We gave them the patch embeddings of every embedding in our data set and gave it to a random forest and a 5 nearest neighbor classifier to see how easily it could classify which sensor did this embedding come from. And we find that in all cases, for both models and both simple machine learning models that are trying to predict them, you can essentially distinguish with almost clean accuracy where an embedding came from, which sensor it came from, which gives us this impression that there is a very clean separation of these things and that there is not a unified response by the model to, say, grass, regardless of sensor. And like I showed in that the slide earlier, the Landsat family and Sentinel-2 and HLS are very closely related to each other. These are all NASA products. Some of them are descendants of each other or mixtures of each other. You can only imagine what happens when you start to add in drone imagery or these other types of data that may be even farther afield than what we've talked about so far. So as the kind of main point of this paper discussion, does this mean that I can't use a foundation model that's pre-trained on a collection that I'm not using for my downstream task? Of course not. What matters is your performance, the task you're working on, and the experimentation that you get done. But what we set out to answer in this question, or in this paper, is does this happen? Does this phenomenon, is it observable? Is it stable across models and sensor types? And what we found is that yes, there is significant differences, and it's important to see how that internal mechanism can impact your performance down the line. And with that, that is my last slide. So I'm happy to take any questions or anything that anyone has about the paper. Thanks, everyone, for letting me present that.
Awesome. Thank you so much. I think you, I was writing down notes the whole time, like, oh, this is so spicy. You're like getting into the reality of these EOFMs, right? Because we're on this cusp of so many of them coming about. You know, my mind was sort of thinking back to the TerraMind discussion back in February that's now released, this like very multimodal approach. And I do wonder, like, how does this perform relative to these just optical examples you have here? So, you know, really interesting. I'm going to open the floor to questions to anyone online. Biplov, go to you.
Hi, Ryan. Thanks for the great presentation. Can you move to the slides where you were comparing the embeddings from HLS and Landsat Sentinel others? Yeah.
These ones?
Yeah, either of these.
Yeah.
So you can see there's like some clear distinction, except if you're using same signal, for example, Landsat 8 versus Landsat 9, right? I'm just curious to see if you have done any experiments where you have just used those patches without the embeddings, just the physical values that's captured by the satellite, and done this comparison to see if HLS, if you plot HLS versus Landsat or Sentinel-2, if you get similar kind of plot, because if that's the case, that's probably explain why these embeddings are separating out, because your source is already in that space. Maybe you can talk a little bit about that.
Yeah, so I have not specifically done that experiment, though I do agree with you that that is likely the source of it. The likely source is that there is some underlying like color distribution differences between each sensor, either in terms of like how each channel is quantized, or just like what types of things the sensor picks up on, or the processing stacks behind them. So yes, I agree with you that that is the source, but I have never generated that figure.
Got it. Yeah, I mean, if I think like 40,000 foot high, and think about like if you're looking at the same object in the ground, whether you use different kind of sensors, it should basically represents the same thing. But again, I guess it comes down to what sensors you're using to capture the data in the first place, right? Yeah, otherwise I don't have any question. Interesting talk. Thank you so much.
Nice. Let's go over to Emil.
Yeah, hey Ryan, thank you for the presentation. I guess to just save slide and just following up on what Biplov was just mentioning as well, and I guess further, I really like the slide too, because it kind of shows, but I guess I think that your conclusion seems to be that the differences in the sensors are essentially bleeding out, or we're seeing that in the embedding space or what have you. And so just to like remind people, even though Sentinel-2's MSI, the multispectral instrument, in theory is designed to be similar to OLI-2 from Landsat 9 or OLI from Landsat 8, et cetera, they don't have the same specs, as it were. That's one thing. The other thing, beyond the fact that the parts of the spectrum that they're looking at aren't exactly the same, other characteristics as well. If you've ever looked at like Sentinel-2 and Landsat imagery over like the same area, you'll generally see that Landsat 8, Landsat 9, et cetera, are imaging, I believe, slightly earlier in the morning compared to Sentinel. And so that's another thing. And then in addition, depending on what's being fed into, say, Prithvi or into DOFA or what have you, one other thing to note as well, if they're feeding in surface reflectance data, if you've also like looked at pairs of like, say, Landsat data taken from the same date as Sentinel-2 data, the Sentinel-2 surface reflectance data actually gets topographically corrected using a DEM. So when you look at like hillshades, et cetera, those areas they look very different from you're going to see in Landsat. We don't have that kind of corrections. And so I kind of wonder if, as it were, they're feeding in different types of data, as you were getting at as well, Ryan, different types of products are being fed in, and then people are assuming, oh, well, they're surface reflectance products. But again, if they're processed differently, because again, Sentinel-2 has topographic corrections, Landsat does not, different times of day, slightly different sensors. I guess too would be like, like planets, planet scope, right? The blue band would necessarily be different from the blue band on Sentinel-2, would be different from the blue band on Landsat 9, etc. And so these things might be coming out, as it were, in your embeddings analysis. But again, it's really cool that you're showing that. And just to say too, the feature space visualization reminds me too of like what folks used to do with Envy, where you could say take multiple bands and kind of just look at spectral signatures of things and kind of turn them around in different dimensions and kind of see where they would separate out or where they would kind of clump together. But really interesting analysis. Over.
Nice. Let's go over to Kyle.
Hey Ryan, I love this presentation even more the second time. I think you maybe digested some of it a little bit more this time around and gave some even better insights, which brings me to something I had not thought about before, kind of bigger picture. What really are the implications or the downfalls of this kind of needing to use the same data in the pre-training of a model if all of the data is freely available and like always being dynamically updated as these public collections are? Like, do you think the implications of like these large pre-trained models maybe has higher consequences in situations where like you've seen the pre-trained models for like high resolution canopy height that like WRI put out, right? That's like pre-trained on like commercial imagery that like everybody doesn't have access to that. Yeah, just kind of wondering if you're, I don't know, just entertain the discussion point there of the implications of pre-training on like large and freely available data versus data that only the data developer or model developers had access to at training time.
Yeah, so this is something that is in the actual discussion section of the paper is elaborated on a bit. Is the implication of this is fairly simply that that simply matching these spectral bands is not sufficient to claim that the model's performance is generalizable across these, and there's probably a lot of implications for somebody could repeat this, I'm assuming, with spatial resolutions and upsample and downsample, something like Sentinel between them, and you're mentioning something like Planet privately trained data. The conversation we're having here in machine learning terms would be one of like overfitting, right? There's a possibility that these models, especially models that are trained on a single collection, are overfit to that collection, right? They learn these symmetries and colors that only apply to that collection, or if they apply to another collection, only do so by chance. What this means, and I tried to put it in the most diplomatic terms, what this means is that your performance is unreliable when you move outside that collection, right? It could work, and it could work because usually the way these models are used is by attaching additional decoders and stuff. But it could work because the decoder is really good, or it could work because the task is not that hard, or it could work slightly differently depending on which collection you pick, right? Like you said, a lot of these data sets are publicly available. You can just, as long as you're within time period, you can just pick to work with HLS or Sentinel-2 or Landsat or, whatever. It depends on what you want to do. And in terms of, data that's not available post-training, there is an even bigger question there of, okay, well, how is that data influencing my performance? Is that, is that problematic in these different ways? And it really depends. The biggest conclusion of the paper is basically that what we would expect, and again, I didn't even include NeurIPS imagery here. We could create a very similar problem, a much worse problem, I'm assuming, with NeurIPS imagery because of the different atmospheric conditions and the lack of, sensor angle and orbit and all that stuff. You can't just match bands and say that, the model's going to tell you whether it's a tree or not, right? It might it might get there because it's not that, because the colors are similar, but there are going to be significant differences between them, which is the big takeaway from the paper, right? Nothing catastrophic, but just that you should pay really close attention to these things, especially if for whatever reason you're moving farther afield to something like Planet or Maxar or these other private collections.
Nice.
Thanks.
Oh, back to you, Kyle. Okay. Yeah, I have a question back to your TSNE. So, this is, I think, yeah, again, a very telling figure. Did you explore UMAP at all, or some other methodology to visualize? Because I guess my inherent question is, I mean, I know this isn't used in your semantic probe, but I just wonder, what we're seeing here, is this a byproduct of the TSNE itself, or is this true? And I had to wager it probably is true, but I wonder if there's also like, by exploring something like UMAP, you see visually, the same sort of behavior. And I wonder what your thoughts on that, and this is maybe going more towards the rigor that you want to apply. You're doing some application with Prithvi, and what's the right methodology you want to sort of bring in when understanding the nuances of your embeddings?
Yeah, so I have kind of two answers to that. One is that the later experiments on these predictions, right? This is kind of meant to show if in the original embedding space, are these actually that easy to partition from each other? So this is kind of another perspective on that other than the visualization. So that's one thing. The other thing is that we haven't looked at UMAP in this publication or there are other forms of this type of analysis. There's a recent publication specifically for comparing foundation models that is called Comparing Data Kernels that we have an open collaboration with the author. And that is stuff that this was kind of like, we kind of packaged this up as its own because we realized it was kind of a small idea with its own conclusion, and it was perfect for this workshop. And it was something we could kind of chip off of our bigger to-do list of benchmarking tasks. So there may be some related things to different types of dimensionality reduction work in future work that Nick and Myskin and I are working on.
Great. Yeah, thanks so much. Because, like, this TSNE, it really does, tell the tale. And I kind of got my gears turning of like, well, maybe if you slice this a different way, it tells a different tale. But of course, that pours out in your direct analysis with that probe. So very cool. Any other questions on the line? Well, I will say, Ryan, Biplov, over to you.
Yeah, maybe one last thought as I'm listening to these discussions. Now that, Ryan, as you're talking about next steps, now that you've established that using different data sets is important and it affects your embedding space, your foundational model and whatnot, maybe the next natural step is to just pick out different techniques like embeddings or fine-tuning, supervised fine-tuning, unsupervised for different kind of tasks, and see if using different embeddings is necessary and to what extent for different kind of activities. Understand, like, depending on whether you're working on high resolution data sets or low resolution data sets, you might have to use different embeddings or different foundational model, but that could be a really interesting work for practitioners, for people like us.
Yep, and we at SIG we definitely agree with that, because we're working on delving deeper into this kind of like practical benchmarking your model for specific use cases approach. So yeah, that is definitely something that we are interested in and actively looking into.
Awesome. Let's go over to Emil.
Yeah, follow-up question. And I thank you also, Tim, for having shared the link to the paper on arXiv. I was also skimming it just now. And I guess that also helps to kind of color a bit the presentation, since I guess there's only so much you can take in through a presentation. So you looked at the embeddings from Prithvi and from Dofa. Are there also thoughts of expanding on this analysis by somehow, is this possible also to look at the embeddings released by Google for their EFM work, or whatever they're calling it now? Just a thought.
Yeah. So there is a couple of problems with that, actually, because we were interested at the start in potentially including that. In terms of the analysis that we conducted for this paper, which is just one perspective, right? It's not the end all be all. There's a problem with including certain types of models, right? What we're looking at is something we'd seen in a couple of publications that have come out in the year or so since the Prithvi paper was published, which is people take Prithvi and they take whatever data they have and they sort of link them together without a question of, oh, this is Landsat data. Is that a problem? So we'll start with the Google embeddings, right? The Google embeddings, we don't have access to the model. So we can't, even if we wanted to, we couldn't vary where these bands come from. And the Google model, the Alpha Earth, as they're calling it now, takes in, actually kind of challenges this analysis a bit by, it takes in both multiple collection levels of Sentinel data and Landsat data at the same time as its inputs. So it is not as easy to map what I'm doing here onto that model, even if we had the weights for it. I bring up that question because TerraMind has a similar question to it. TerraMind takes a multimodal approach where it basically separates out the encoding of each patch, right? So you'd have to, if you wanted to bring in a model like that, and there's more than just TerraMind like that, this is kind of like the new iteration of these models is kind of taking this approach. In many cases, there's TerraMind, there's a model named Galileo, there's something called OmniSat and AnySat. These are all basically, like, I would say, the second round of the EOFMs that all cite the first round. You could attack this analysis in a very different angle. Those publications are all brand new. Some of them don't have public weights, and you have to kind of, figure out a way to answer that question with those models. But this is just to sort of look at a specific workflow that we've talked about, or that we've seen in practice with how other people are working with these published works, right? Whether the published works, I would not say that any of these works implied that you can do this, really. They didn't come out and say explicitly, oh, use this for any satellite data you want, but to address a way that it is being touched on by the community.
Awesome. No, thank you. That's helpful to know. And I guess, as you said, where your bigger question, as it were, is kind of understanding the differences between the different foundation models and how useful they are. I'm guessing too, and probably you and team have already thought about it, but I guess other ways of, say, attacking the problems of attacking the question of the utility by perhaps evaluating accuracies of, say, downstream types of products, which would then, I guess, make it easier to say, like, because then you could actually pull the outputs from Alpha Earth that are published, et cetera, and just use those. But again, I guess kind of like that bigger question that you're looking at. But again, thank you for sharing this with us. Definitely illuminating. Thank you.
Yeah, and we absolutely want to get into more of that stuff. The workshop paper, being only 4 pages, definitely limits the amount you can pack into it in terms of what experiments can be run. But it's nice because it's, like I said, it's a very self-contained kind of problem that we can say, okay, well, now when we write another paper, we don't have to include these 4 pages.
Wonderful. I mean, that was a fantastic discussion. Any other thoughts on the line? Well, I'm going to hold you to this, Ryan. You and the wider team, as you guys are chipping away at these next bigger questions that you're getting at, you're talking about this next wave of EOFMs and sort of these more complex or exotic type of models. I know you guys are thinking about this both at the application stage and also really sort of the underlying embedding space stage, So as you guys are doing more, we're going to continue invite you guys. So keep the line open about what you're working on, and we'd love to have your thoughts about sort of what you're up to, because it really does benefit this working group. Really insightful discussion. I appreciate it, and I think this is going to be a big hit on our YouTube channel. Thanks everybody. Thanks Ryan, and we'll talk in 2 weeks.
Thank you guys. Yeah, we'll always happy to be back whenever we've got new stuff coming out.
Love it.
Thanks everyone. Bye.
Thanks, guys. Thanks, Ryan.
Bye.